Hi Math 242. In this video we're going to talk about section 13.3, which is solving a special kind of an equation. And the equations in this section that we're going to be solving are what are called differential equations. And let's first talk about what a differential equation is, and then we'll work out how to find them. So a differential equation is an equation, and it contains an unknown function and one or more of its derivatives. So remember that the most important thing is this is an equation, right? So it's going to have some sort of equal sign in it, okay? And the other parts of this are that there's going to be a function and some derivatives, right? So for example, I could write a differential equation. Maybe that would look something like f prime of x equals 2x times f of x. Okay, so notice this is an equation. It involves a derivative, and it involves x and a function of x. So it's an equation that involves both derivatives and the function itself, and it can include the independent variable x as well, right? Another way we could write this would be written as, we could write this as dy dx, or a derivative equals 2xy. Okay, and these two differential equations actually say the same thing, because it says derivative equals 2 times the independent variable times the dependent variable. Okay, so these two equations actually say the same exact thing. They're just using different notation. But this is an example of a differential equation, and they can be as complicated as you want. You could have something like y double prime, the second derivative, plus 2y prime plus y plus 4 equals 16 or something. That's an equation. It involves a function here, y, right? Y would be a function of x maybe or something, and some of its derivatives, okay? And so these are all different examples of differential equation, and what we'd like to do is categorize them or be able to tell how they're different, right? And one way we can do that is to do what's called ordering them. And so we say the order of a differential equation is the order of the highest derivative found in the equation, or the power of the highest derivative found in the equation, right? So notice in these first two, the highest derivative found in the entire equation is 1, right? So what that means is that these two are first order, right? Because the highest power is the first, or the highest derivative is the first derivative found in each equation. This one right here, this would be considered, the whole thing that is, this would be considered a second order differential equation. The reason for that is because the highest derivative, the highest order derivative that's found, is this second derivative right here, okay? Now, these are equations just like we've worked with before, right? We've worked with equations, something like x squared plus 2x plus 1 equals 0, right? We've worked with an equation like this, and we've been able to solve an equation like this before, right? Remember what it means to solve an equation like this. It means to find an x that satisfies it, right? Okay, so that means find an x that you can plug in here and it'll make a true statement. Well, what we can do is do the same exact thing with a differential equation. But instead of finding a value of x, a number for x that we're going to plug in and have it work, have it make a true statement, instead what we're doing is we're plugging in functions, right, and derivatives in order to get a true statement. Okay, so this, for example, this second order equation says that if you had some sort of a function, if you plugged its second derivative here as an expression, you plugged its first derivative here as an expression, and you plugged itself as the function here as an expression, and you worked all of that out in terms of arithmetic, you would get 16. Right? Maybe all the variables would cancel or something like that, and you would just get a number as a result, right? Okay, so we can do similar things with these differential equations that we've done with these regular equations we've seen before, okay? And that involves solving them, right? So let's see what a solution means for a differential equation. It's going to be a function, right? So a function is a solution of a differential equation if the equation is satisfied when the function and its derivatives are plugged into the equation, okay? So just like we say we use this word solve, or x is a solution to the equation if you plug it in and everything works out nicely, so we say a function is a solution of a differential equation. Okay, so let's first see if we can tell if we actually have a solution first. And I wanted to show that we had an example here, but my paper has disappeared. Oh yes, here it is. Okay, so let's work our example. So let's make sure that we can be able to tell that we in fact do have a solution. So I'm going to be working on a problem from our textbook. This is going to be number 35 from this section 13.3. This is on page 728. Okay, and it asks us to show that this y equals the square root of c minus x squared is a solution to this differential equation. Dy dx equals negative x over y. Okay, we want to show this is a solution to this differential equation. Okay, so how do we show that this function right here, this y equals square root stuff, is a solution to this? Right? Well, remember what it means to be a solution. It means that when you plug in the function and its derivatives, it works, right? It satisfies the equation, right? Okay, so what does this mean? This means that over here on the left-hand side, I need to plug in the derivative of this thing, right? I need to plug in the derivative here. Okay, I need to take the derivative of this y equals thing and plug it in there. Okay, where else did I need to do? I need to take y and plug it in here. That's the name of the function. Okay, so first we better start out by finding dy dx, right, for this potential solution, and then we'll plug that in there, and we'll plug in the value, the expression for y down here, and see if it works. Okay, so let's first take the derivative of that square root thing. So we had y equals the square root of c minus x squared. Let's write dy dx. So that means the derivative of this thing, right? Okay, so remember that this is actually c minus x squared to the 1/2. Yeah. Okay, so what we can do now is apply the power rule and the chain rule to get the derivative. So 1/2 c minus x squared to the negative 1/2 times negative 2x because of chain rule. And if you like, we can simplify that down to dy dx is, let's see, 2's cancel. I have a negative out front, so this is negative x in the top over square root c minus x squared. Okay, and if you need to write more steps than that, to go ahead and pause for a second and do more steps, but your answer should look like this for the derivative. Okay, so now we want to take that expression for dy dx and plug it into our differential equation. Okay, so remember our differential equation looks like dy dx equals negative x over y. Okay, so this is that derivative right there that I'm going to plug in on the left side of the equation. I'm going to take this whole thing and put it right there where the derivative is. And then I'm going to put the square root stuff here for the y. And I'm going to check to see if I get equality. Okay, so let's see, dy dx. I'll actually write it in pink so you can see that what I'm plugging in on the left-hand side. So I'm writing dy dx. That's dy dx, okay? Now I want to say, does that equal negative x over, and I'm going to plug in y. What was y again? It was the square root of c minus x squared. Okay, that's dy dx on the left. This is y in the denominator. Is that true? Do we get equality? Are those two things equal? Yes. Since they are equal, that means that it is a solution, that the equation y equals, or the function y equals the square root of c minus x squared is a solution to this differential equation right here. Dy dx equals negative x over y. Okay, well that's all well and good, but how do we go about finding a solution? Okay, this we're only going to consider a couple of kinds of differential equations because quite honestly they get really complicated very quickly. So we will only be able to find solutions to these two kinds of differential equations that I've defined here. So the first one is a simple differential equation, okay? And a simple differential equation is of this form where you have dy dx equals an expression of x. Okay, when you have dy dx equals an expression of x, that's called a simple differential equation. Alternatively, a separable differential equation is of this form. Dy dx equals an expression of x times an expression of y. Okay, so there might be like mixing of the variables, but only in multiplication. It has to be expression of x times an entire expression of y. Okay, and let's see, the one we just did before, the differential equation we just did before, this dy dx equals negative x over y. Is this one simple or separable? Well, let's look at our definitions. Simple means it's dy dx on the left, good, we've got that, equals only expression of x on the right. Are there only x's on the right-hand side? No, right? So because there's not only x's over here, that means this can't be a simple, right? So this is not simple. Okay. All right, well, let's consider if it's separable. So a separable one says dy dx on the left, got it, equals expression of x times expression of y. Well, does the right-hand side look like expression of x times expression of y? Maybe. If you rewrote it, you don't have to rewrite it like this, but you can see it actually like this. There's an expression of x times an expression of y, right? Isn't it true that when you multiply these two things, you get negative x over y? And this says expression of x, expression of y, okay? So this is in fact separable. Okay, so we actually have already observed a separable differential equation, we just didn't know it. Okay, so how do we go about solving each of these two forms, right? So maybe I should just outline this for you. So solve a simple, in order to solve a simple one, they're called simple for a reason. Okay, in order to solve a simple differential equation, you just have to you have to undo the derivative, right? If it says dy dx equals an expression of x, right? This is stuff you've seen before. Dy, like for an example, dy dx equals 3x squared plus 2. How would you find a function that satisfies this differential equation? Well, it would be the function that says my derivative is 3x squared. You'd be able to figure out what that function is that satisfies that by doing what? Undoing this derivative, by doing an antiderivative. So you could get the solution by just doing an integral, right? So the solution would be found in general, if you want to say in general, and then maybe we can do this example, but the solution would be found in general by saying, well, y, the function that is the solution, is found by doing the integral of the right-hand side, f of x. Okay? So for example, here, if we have dy dx is 3x squared plus 2, then y would just equal the integral of 3x squared plus 2 dx, okay, which is, of course, what? X to the third plus 2x plus c. Okay, and so this right here, this would be a solution to this differential equation right here, because that is a function that says, oh, you put my derivative here, you get equality, right? My derivative is 3x squared plus 2. Okay, those simple ones are fairly simple, that's why they're called simple. The separable ones take a little bit more work, right? So solve separable. Okay, so to solve a separable one, we have to use this word. We have to separate the variables. Okay, so if we have dy dx like this, and it's some sort of expression of x times some sort of expression of y here, I want to separate the variables. I want to get all the y stuff on one side and all the f stuff on the other side. Okay, so what that means is that I need to move this g of y thing down, and I need to move this d of x thing up. Okay, so if I sort of draw some little arrows about where things are going, this needs to go down and this needs to go up, right? Okay, so I'm going to write this as, let's see, I divided by g of y, so this is dy over g of y. I brought that down, and that equals f of x, and bring the dx up. Okay, we don't usually like to see this on the left-hand side because we like to emphasize how important this dy and dx are, so usually we'll write it as 1 over g of y dy equals f of x dx. Okay, and to actually undo the derivative, because remember this says derivative equals something, right? We're going to have to undo this derivative at some point. To undo it, we now say, okay, we've got everything separated, now apply indefinite integrals to each side. Okay, so you're going to do two antiderivatives. You're going to do an antiderivative on the left side and an antiderivative on the right side. Okay, so again, the simple ones, really straightforward. You just do an antiderivative. The separable ones, you first have to separate the variables and then do an antiderivative on each side. And after that, you would want to make sure that you solve that for y equals, right? Whatever your answer is in this line when you do the antiderivative, you want to get y equals all by itself. Okay, so let's maybe do one example here of a separable, since we've already done a simple one, right? We just did an antiderivative. Okay, let's see, let's solve a differential equation that looks like this. Let's do dy dx equals x e to the y. Okay, so is this simple or separable? Well, notice that there's y stuff on the right-hand side, which means this is not simple. It is a separable differential equation because it says expression of x times an expression of y. Okay, so let's separate things. I'm going to move the expression of y to the denominator, so 1 over e to the y dy equals, and I move the dx up, x dx. Oops. Good. All right, so now what do I do? Remember, I have to undo the derivative, so go ahead and add some integral signs right here to say I'm going to do an antiderivative, but with these separable ones, remember you do an antiderivative on each side. Okay, so on the left-hand side I have e to the, this is negative y dy, and on the right side I have integral x dx. Okay, so how would we do each of these two things? The right-hand side we could do, right? It's just a reverse of the power rule. Okay, we would get x squared over 2, and then we could do a plus c, right, because it's an indefinite integral here, an antiderivative. On this left side here, what do I do? Well, this, notice, is not plain old y here. The antiderivative here is not just e to the negative y, right? Because there's something different going on up here in this power. So perhaps we should think about this one a little bit more carefully. Let's go to maybe a piece of scratch paper here on the next page, and we'll just do a little work here. This one would be beneficial to use a u substitution because there's something that we don't like up in the exponent. So let's let u equal negative y. Then du dy is equal to negative 1. So what do I get? I get du equals negative dy, or dy equals negative du, right? Okay, so what that means is I can replace this with e to the u, and dy is negative du. Now that's not a subtraction, that's a multiply, right? Which means I can bring this out as negative integral e to the u du, and the antiderivative is then negative e to the u. But I got to plug the u stuff back in, so negative e to the negative y, of course, plus e. Let's take that result back to the other page. So this is negative e to the negative y plus c. Should I put another one over here on the left side like this? Or can I just put one big plus c somewhere? Because if I just have two constants somewhere, one on one side, one on the other, they could just combine to make one big constant. So let's only keep one on this side. Great. So remember, the last thing I told you about solving a separable is that your last step here needs to be to get this answer from the antiderivatives in terms of y equals. This one currently does not say y equals, right? But I could get it to say y equals. Okay, let's try to isolate that y. So first, get rid of the negative in front. I have e to the negative y equals negative x squared over 2 minus c. Who cares? It could have been stayed a plus because that constant, remember, is just an unassigned number. And how do I get a y, an unknown thing, out of the exponent when it's in an e like this? Remember, you have to make use of ln, right? So I have negative y equals ln of negative x squared over 2 minus or plus c. It doesn't really matter. I'll keep it a minus just to keep you happy. And so now I can get y equals by multiplying or dividing both sides by a negative. So I get y equals negative ln of x squared, negative x squared over 2 minus or plus c. It doesn't really matter because it's just an unassigned constant. Okay, and that is our solution to our original differential equation. Okay, again, how would this work? This is the function that you can plug its derivative here, and you can plug itself up here, and you'll get left side equals right side, right? It'll satisfy the equation. Okay, so the last thing is that this is what's called the general solution whenever you have a plus c like this, right? What we can actually do is make use of these words general and particular that we've had before to say that this is the general solution to this differential equation. But if we had another piece of information about this function y right here, if we knew a point it passed through or something, then we could actually find the particular solution and actually get a specific value of c, right? And so just for your own practice, maybe, why don't you find the particular solution for this function here passing through the point, let's just say for fun, let's say it passes through the point 1, 0. Let's say 1, 0. Okay, so find the particular solution, meaning find the function with a specific value of c that passes through the point 1, 0. Again, that means replace x with 1, y with 0, and solve for c. That'll give you the particular solution. Good. We will continue with some problems in class.